Hello, and welcome to an introduction to the concept of the mean or average value of a continuous function on a closed interval. We're going to start with the very basics. As you can see, we have some group of pennies. There's a group of 3, a group of 8, and a group of 4. And if you had been asked way back in the day, what was the average number of pennies across these groups, you would have done the thing that you've done for many years, which is to add the 3, the 8, and the 4, get 15, and divide by 3 because there are 3 groups, and you would get a mean of 5. But what we don't often stop to think about is the question that the mean is actually designed to answer. And the question that the mean is designed to answer is, if we were to apportion these pennies equally across the 3 groups, how many would each group get? And the answer, of course, is 5, and that's the mean. So that's what means are intended to address when we're talking about numbers of items in finite sets. How many would each get if they all got the same? Now we're going to switch to Desmos, and we're going to take a look at what that might mean in the case of a continuous function. So here we are on Desmos, and I have here the graph of the sine function from x equals 0 to x equals pi. It's a very familiar shape. So it, of course, tops out at the point pi over 2, 1, and there it is. The question of the average value of this function on this interval goes like this. We ask ourselves the question, what would happen if we were to preserve the total area under the curve, but flatten it out so that we were looking at a constant function? Or equivalently, what constant function on the same interval encloses the same area as the sine function? So that's the notion. We want to know what happens if we compare these two functions on the same interval, a constant function and the function that's before us, and we require that they enclose the same area, or as we'll see a little bit later, the same net signed area. That's the idea. And so now the question becomes, how do you calculate the average value of a function? And it turns out that it's rather similar in spirit to what you do when you take the average of a group of integers. So we're going to switch back to the .chem and see how that works. So the calculation that we need to do follows immediately from what we just said. We want to find some constant that has the property that that constant function on that interval encloses the same area as the sine function. So we want the integral from 0 to pi of some constant function, we'll call it k dx, to be equal to the integral from 0 to pi of our function, sine of x dx. And we just have to figure out what is the k. Now, this is just a rectangle, right? I really didn't need to go to all the fuss of writing an integral, but just to show that ultimately this is what we're doing, and we're equating two integrals. This is just the rectangle with a height of k and a width of pi minus 0. So this is k pi. The right-hand side is going to take a wee bit more work. We need to anti-differentiate, which gives us op cos x. That is from 0 to pi. And then we have k pi equal to, let's see, op cosine of pi. So the opposite of -1, which is 1, minus the opposite, so plus the cosine of 0, which is also 1. And so 1 plus 1 being 2, k is 2 over pi, which is about 0.637. And if we go back to Desmos, which we'll do in a moment, you'll see that that's a very plausible number given how the picture looks when we morph it into the constant function. If we think more generically about a formula for the average value of a function, it flows from a similar process. So if we have some continuous function f on closed AB, then we need to be able to integrate from a to b, whatever that constant is, and have that be equal to the integral from a to b of the function. This is still just a rectangle, right? This time it's k times b minus a. And of course, on the right, we have whatever the integral from a to b of f of x dx may be. And if we just divide by b minus a, we have a formula for the average value. So it's 1 over b minus a, integral a to b, f of x dx. And typically, you call that f average or g average or whatever it may be, depending on the name of the function itself. So it's similar actually in spirit to what we do when we find means of integers, because basically we've got some sort of sum. In the more familiar case, it's the sum of a bunch of numbers. In this case, it's the sum of a bunch of areas of Riemann rectangles. And then we're dividing by some measure of the magnitude of the situation. And in the discrete case, that's just the number of values. And in this case, it's the length of the interval over which we're considering the function. So if you sort of keep that correspondence in mind, it's a bit of an aid to remembering how this formula works should you ever forget the details of it. Let's pop back to Desmos. As you'll recall, we said a moment ago that the average value of this function is about 0.637. And if I flatten it out like so, that's what it looks like. Here's 0.5, here's 0.6. So just shy of halfway from 0.6 to 0.7, 0.637 seems quite a reasonable estimate. A question we might want to answer before we finish is, what happens if a function gets negative? Can the average value of a function actually be negative? And I'm going to switch to another function that is negative for a portion of its time on the interval, and we'll see how that looks. So here is the graph of a cubic. It's actually f of x equals quantity x minus 1 times quantity x minus 2 squared. And as you can see, a portion of the area between the curve and the x-axis is negative. And in fact, it looks as though there's more area below than above, which would lead you to conclude that the integral from 0 to 3, that's the interval, closed 0 to 3. The integral from 0 to 3 would in fact be a negative number. And if I then divide that by the length of the interval, which is always going to be non-negative, I should get a negative absolute value. And in fact, if I locate my slider here and morph this function as we did the previous one, you'll see that we do indeed have a negative average value. It looks like it's somewhere between 0 and negative 1, negative 2/3, something like that. If you wanted, you could try to figure out exactly its value and compare it to this picture. So I hope this quick introduction to the notion of the average value of a function, continuous function on a closed interval, has been helpful. And everybody, happy mathing.